Hello viewers, welcome to video tutorial on potential due to spherical charge distribution. I am Dr. P. Ramakrishna, Assistant Professor of Physics, Government Degree College, Kamareddy. Concept of potential due to spherical charge distribution forms a part of chapter Electrostatics in Electromagnetic Theory paper of BSc Physics syllabus. In this video tutorial, we are going to learn how electric potential due to spherical charge distribution can be arrived. In text, we will find different ways of deriving this expression, but according to our syllabus, it is given that we have to derive it from electric field intensity. So in this video tutorial, only that type of derivation is provided, that is derivation of electric field potential from electric field intensity. It is mentioned as an application. We will study accordingly. And another thing, we have two cases here. Coming to spherical charge distribution, the distribution may be either uniform spherical charge distribution on non-conducting insulating material, or it could be on conducting material either. In the case of conducting material, the charges will reside only on the surface. So, that type of arrangement will be equivalent to shell, spherical shell. We will see in two cases. First one, uniform spherical charge distribution of charge, that is insulating sphere, non-conducting or insulating sphere. In the second case, we will see spherical shell. Let us see one by one. First, let us have a quick recap of what we have learnt in the previous slides, previous tutorials. First one, electric potential. These things are essential for our current tutorial. First one is electric potential. We know that electric potential at any point in the electric field is defined as amount of work done in bringing unit positive charge from infinity to a point in the electric field. Mathematically, it can be expressed as V is equal to W by Q naught. Here VA stands for potential at point A. Q naught stands for unit positive charge, or sometimes it is also called as test charge. W is the work done in moving the test charge. The next one is potential difference. Potential difference can be expressed as the difference in the electric potentials between 2 points. Here in this expression, it is assumed that the potential difference is expressed between points A and B. VA minus VB stands for potential difference between points A and B. So it is defined as amount of work done in moving test charge Q naught in between points A and B. The units of electric potential and potential difference is volts, that is they are measured in volts. Next, let us see the relations between electric field intensity and the potential. These are very much useful in our derivations. First one is integral form. Here it is expressed as the electric potential is equal to minus of integral E dot dl. The same form in a converse way, in a reverse way, can be expressed as differential form, that is electric field intensity E is equal to negative gradient of potential. that is E is equal to minus of del V. Here this is del operator. It's an operator. It is operating on vector, on scalar potential and converting it into vector field intensity. Next one is potential energy. Potential energy of system of charges is expressed as it is nothing but the amount of work done in assembling that system of charges. So W is equal to the amount of potential energy PE. It is equal to half times summation over VI QI, where I stands from 1 to N. Next one is energy density. In energy density of an electrostatic system is given as U is equal to half times epsilon naught E square, where epsilon naught is the permittivity of free space and E is the electric field intensity. We are going to use these equations in our current derivation. Now let us come back to our current topic, that is potential, electric potential due to spherical charge distribution. Let us first take up electric potential due to uniformly charged sphere. Let us assume an insulated, that is non-conducting solid sphere of radius r, capital R, and has uniformly distributed total charge q. Observe the figure. Here the centered circle denotes the insulating sphere with center at O, having radius capital R and a uniform charge distribution with total charge plus Q. That means on every point this charge plus Q is distributed uniformly within the sphere. Okay. Now here we get two cases. In our in standard textbooks, potential is calculated either outside or inside. But in our local textbooks, we observe three cases, that is outside, on the surface and inside. Here I will give the derivation for only two cases, outside and inside. The third one, on the surface, I'll explain. It can be written very easily. Let us see first one, that is outside the sphere. Let us assume point here. Let us assume point here with distance small r greater than capital R. It shows that the point is outside the insulating sphere. Now let us derive the electric potential at this point. For this we use Gauss law. According to Gauss law, the electric field intensity at this point is expressed as E is equal to 1 by 4 pi epsilon naught times Q by R square. We know that. Also, we know that there is a relation between field intensity and the potential, that is V is equal to minus of integral from infinity to R E dot dl. This is nothing but amount of work done in bringing the unit positive charge, that is any positive charge, from infinity to this point. Infinity to this point is called as potential at this point. Now let us substitute the value of E in this equation. Remember this equation. Again it is reproduced here. Let us substitute the value of E from the previous equation. So if we substitute, we know that Q by 4 pi epsilon naught is a constant. Only the variable in the expression for electric field intensity is R. So we can write it outside the integral. Now if we integrate this one, integral 1 by R square is nothing but minus 1 by R. And the limits are from infinity to r. If we substitute the limits, in the first case, upper limit will be r only, so 1 by r, and lower limit will be in infinity, 1 by infinity. Minus into minus becomes plus. Okay. So again, if we look at this equation, 1 by infinity is equal to 0. So this second term becomes 0. We will remain with only one term, that is v is equal to 1 by 4 pi epsilon naught times q by r. So we can say that, if you remember, this is nothing but the potential due to point charge. We have derived this in the previous tutorials. So we can say that for uniform spherical charge distribution, if we consider a point outside the sphere distribution, then the sphere or distribution appears as if entire charge is concentrated at the center. Now the second case may be, sometimes in our local textbooks, uh, other case will be given. This is the case outside the sphere. Third case, on the surface. On the surface, in standard textbooks, on the surface case is not mentioned. If anybody wants, he can do apply limits instead of r, small r, he can apply capital R. So you will get a equation, the final equation as q by 4 pi epsilon naught times 1 by capital R. Okay. Again I am repeating the second case as per our local textbooks. The second case as per our local textbooks, that is point of observation on the surface of the distribution. In that case, it becomes V is equal to, potential V is equal to 1 upon 4 pi epsilon naught times Q by capital R. But in standard text, it is not mentioned as a separate case. Okay, now let us move on to the next case, that is point inside the sphere, that is small r less than capital R. In this case, the Gauss law, we can say that according to Gauss law, the electric field intensity is E is equal to 1 upon 4 pi epsilon naught times Q by Q R by capital R cube. But when we want to find out electric field potential is nothing but amount of work done in bringing a unit positive charge from infinity to a point in the field. That means we have to bring it from infinity to small r, which is present inside the sphere. Now what do we notice here is, outside the sphere the expression for electric field intensity is different, which we have seen in the previous slide. Inside the sphere the electric field intensity expression is different. So we have to split this according to boundary condition. We have to split this integral into two terms, one from infinity to surface of the distribution, that is infinity to capital R, surface of the distribution. Another one from the surface of the distribution to the point inside the distribution, small r. Okay. Now you know the values. Outside the distribution it is just 1 upon 4 pi epsilon naught q by r square. Okay. Inside it is mentioned here. This we have seen in the previous slides. Okay. Now if we integrate this, we get, we know that 1 by r square is nothing but minus 1 by r, and here it will be r square by 2. Integration of r dl will be r square by 2. So After integration and substituting the limits, this we have seen in the previous case, this will become q by 4 pi epsilon naught times 1 by r. But in this case, if we look in this case, this will become r square by 2. So 1 by 2 is written outside, and after application of limits, it is becoming r small r square minus capital R square. Now here we have to sum up these two terms. Be careful while summing up. Now here if we take cube by 4 pi epsilon naught times 1 by r common from these two terms. I am repeating, we are taking common this term. We are taking common this term from two terms. So in the first term we will get only 1, but in the second term we will get 1 by r square. When we multiply that 1 by r square inside this bracket, it becomes small r square by capital R square minus 1. Okay, minus this minus into this minus becomes plus. And if we sum this, here again my 1 by 2 is there. So in the bracket it will become 2 minus r square by capital R square plus 1. So after summing up all those things, we will get this equation. Okay. So this is equal to q by 4 pi epsilon naught times 1 by r times 3 minus r square by capital R square. At the center of the sphere, that is when small r becomes 0, this second term, entire second term becomes 0. In that case it becomes v naught, that is nothing but at the center, just only 3 will remain in the bracket, 3q by 8 pi epsilon naught r. So this is the derivation for uniform spherical charge distribution. Potential due to uniform spherical charge distribution outside as well as inside. Let us quickly look at how it will be. Graphically, let us see. Here the distance is taken on x-axis, potential is taken on y-axis. If we plot the graph, we have seen in the previous slide that inside the spherical distribution, potential is varying like this. It is slowly as r increases, as small r increases, the value of potential slowly decreases as shown in the curve. At the center, the value is this much, 3q by 8 pi epsilon naught r. At the center, this is the maximum value. So for uniform spherical charge distribution, the maximum value of potential will be present at the center of the distribution. As we move away from the center, the potential value drops. Inside the distribution or inside the surface, the variation of potential will be in this form according to this equation. Okay, but outside it will be in a simpler form. It varies inversely to the distance r. Have a quick look here. Outside it is varying inversely proportional to r. On the surface it is constant, but inside the boundary, inside the distribution, it is maximum at the center. As we move away from the center, it slowly decreases. The value of potential at the boundary, that is at the surface of the distribution, boundary of the distribution, will be 2/3 of its maximum value, that is at value at center point. So this is all about the electric potential due to uniform spherical charge distribution. Now let us move on to the next one, that is shell. Let us see how it will be in the case of shell. Shell means the charge will be present only on the surface. Inside the sphere, inside the boundary, there won't be any charge. It could be either shell, it could be either shell or conducting sphere also. Even in the case of conducting sphere, the entire charge resides on the surface of the sphere. So it will be equivalent to shell. Let us see in this case. Again, let us assume similar one. A sphere of radius capital R. The electric field inside the spherical shell will be 0, which we have learnt in the previous slides. Outside the shell, it appears as if the entire charge is concentrated at its center. This we have learnt in the previous slides. Now, previous tutorials, not in this tutorial, previous tutorial. Now let us consider the point outside the shell, outside the boundary. We know that the electric field is given by E is equal to 1 by 4 pi epsilon naught times q by r square. For outside points, shell as well as uniform charge distribution, both are one and the same for outside points. Okay, only the difference comes inside the boundary, inside the shell. So this a derivation will be similar to the previous one. So I am not going in detail. You can look into previous slides. So the same expression will come for outside point, that is V is equal to Q upon 4 pi epsilon naught times 1 upon R. So we can say that even the potential, even for the case of potential also, the entire charge appears to be entire charge of the shell, which is actually present on the surface of the shell, is appears to be concentrated at the center of the shell, at the center point. Though uh, no charge is present at the center of the sphere shell, it appears as if the charge is present at the center. The entire charge is concentrated at the center of the sphere for the points outside the shell. Okay. Now let us look into the inside shell. Even for on the surface, again I am repeating, even for on the surface, the same derivation will continue. Only the change is, instead of small r here, we take capital R. Then the final expression becomes q by 4 pi epsilon naught times 1 by capital R. Okay. Now next one, that is inside. We know that for a shell, the electric field is 0. The electric field is 0 inside the shell. Now let us see what happens for potential. Again, in order to find out the potential at a point inside the shell, we have to uh, divide the integral into two terms, that is from infinity to the boundary capital R and from the boundary to the point inside the shell, because the value of E differs in these two regions. Okay, if it would be had it been the same, we would have continued with the single integral, but the value of E differs in these two regions. That's why we split the integral into two separate terms. We know that outside the expression is this one we have seen in the previous slide, but inside the electric field is 0. That means this entire second terms goes to 0, becomes equal to 0, nullifies. So we will remain with only this term. So that is nothing but q upon 4 pi epsilon naught times 1 by capital R here, which is equivalent to the potential present on the surface. Okay, so this is nothing but here. If we look the potential graph, it will be like this. Let us assume that this is a shell of radius capital R. outside the shell, outside the shell, the potential is inversely varying with the distance or with the radius. But inside the shell, the potential is constant, which is equal to the potential present on the surface of the shell, the potential present on the surface of the shell. So with this we have completed even the shell also. What the difference we notice is outside the shell, outside the distribution, for shell as well as for uniform insulating charge distribution, uniform charge distribution on insulating body, the derivation is same. Potential varies inversely proportional to R, but inside it differs from shell to uniform charge distribution. In the case of shell, the potential is constant inside, but for uniform charge distribution it is maximum at the center and decreases with some function, okay, which we have seen in the previous. Now let us look at small problem which is frequently asked in university examination. The question is, what is the electric potential at the surface of nucleus of gold? The radius of nucleus is 6.6 Fermi and the atomic number of gold is 79. Here it is given that charge is mentioned and radius is given. Okay, Q and R is mentioned and we are supposed to find out the potential. When Q is mentioned, the atomic number is given. When atomic number is given, the total charge becomes Z times E, where E is the charge present on electron. So 79 times 1.6 times 10 raised to minus 19 coulomb will be the total charge present on the gold nucleus. Okay, and the distance, the radius of the nucleus is 6.6 Fermi. We know that Fermi is equal to, Fermi meter is equal to 10 to the power of minus 15 meter. On substitution and simplification, we get the value of potential as 17.2 times 10 raised to 6 volts. Okay. Mostly you will get long answer question in this topic, that is derivation of potential for uniform spherical charge distribution as well as shell. Sometimes numerical problems are asked like this. Let us see some of the questions for assignment. Assignment is first one, a spherical drop of water carrying a charge of 3 times 10 minus 10 raised to minus 6 coulomb has a potential of 500 volts at its surface. What is the radius of the drop? It is similar to the previous one. In the previous case, radius is given and potential is asked to find out. Now here in this problem, in the first problem, potential is given and you are supposed to find out the radius. Same formula you will apply, do it. You can do it very simply. Next one, two concentric spheres of radii capital R and 2R have charges 1 microcoulomb and 2 microcoulomb respectively. That means there are two spheres having same center with radii R, capital R and 2R. They have the charges as 1 microcoulomb and 2 microcoulomb. The potential at 3R is given. That means outside the spheres, for both the cases outside the sphere. The potential is given as 9 kilovolts and it is asked to find out the value of radius R. It's very simple. Here we have two spheres, concentric spheres, and a point is given outside of two spheres. So the total potential at that point will be equal to sum of the potential due to those two spheres. If find out the potential due to first sphere as well as due to second sphere, you will get expression in terms of R, capital R, and the potential value is given, that is 9 kilovolts. Substitute the value of potential and get the value of capital R. Next question, if two concentric conducting shells of radii R1 and R2, where R2 is greater than R1, carrying uniformly distributed charges Q1 and Q2 respectively, find the potential at the surface of the shell. Now here surface of the each shell is given. Okay, we have two spheres having same center. R1 and R2 are the radii. Charges are Q1 and Q2. You have to find out potential on each surface. For outside surface, that is with radius R2, surface potential will be constant, you know that, and there will be contribution from inner sphere also, which you can find out q by 1 4 pi epsilon naught times 1 by r. So substitute that and sum the two values. In the case of inner shell with radii r1, on the surface it will be constant, you can calculate it very easily, but there will be contribution from outer sphere even. So you have to apply the constant value, because it is shell, it is not uniform sphere, uniform charge sphere, it is shell. The potential inside the sphere is equal to the value present on the surface. So it appears to be complicated at a first look, but it's very simple, you can do. Okay, with this we have completed this tutorial, that is for electric potential on electrical potential due to spherical charge distribution. Thank you for watching the tutorial. Please follow our channel.